All right, welcome back, physics friends. Today we're going to look at a two-body incline problem. So I've drawn our setup. I have not yet done the free body diagram because I want to show you how we do this one. So we have two blocks, both with a mass of 8 kilograms. So I'd labeled this one M1 and this one M2. The surface is rough, so it has a coefficient of kinetic friction of 0.22 and the angle theta is 37 degrees. Now there is a pulley in here, but I'm going to say that this pulley is massless and frictionless, so we don't have to account for it. Now, if you've done rotation and it talks about the pulley having mass, then you definitely need to account for it. But what we're going to look at is a little bit more simple here. So with this system, because these two objects are connected, so they're going to move together, they're going to have the same acceleration, I want to know what the acceleration of the system is and what is the tension in the string. So the first place we start is to make a free body diagram, because when in doubt, free body diagram it out. So I'm going to start by drawing in the force of gravity, and there's a force of gravity acting on each box. So I'm going to give them specific labels. So over here, because I call this mass 1, I'm going to call this FG1. And over here, because I call that mass 2, I'm going to call this one FG2. Okay, and then we have a normal force on the incline, perpendicular to the surface. No normal force over here because that's not on the surface. Okay. We have tension in the string. So tension in the string. I have tension pointing up the string here and tension pointing up the string here. Now, because this pulley is massless and frictionless, I can say that these tensions are the same. The string is ideal. Okay, now if this pulley had mass, that wouldn't be true, because in order to get something to rotate, you need to have an unbalanced torque acting on it, so your tensions can't be the same. But in this case, we're not worrying about that. And then that's all the forces on my hanging block, but on my block on the incline, I have a few more to worry about. Because the surface is rough, and because this block is going to fall down this way, and this block is going to slide up the incline, I'm going to have friction that points down the incline, like so. And then I'm going to add in over here my components. So I have my FGX pointing down the incline, and I have my FGY pointing perpendicular to the incline. Okay, now we're ready to go. Now with this free body diagram, I can set up a system of equations to solve for the acceleration. And if you've never done this before, this method might not be familiar to you, but to be honest with you, when I was a student in high school, these were really challenging for me. And then when I became a teacher, I learned this method from a teacher that has had way more experience than I, and it made it so much more simple. And now these problems are so fun. I just love them. So let me show you how we do this. So we think about the different objects. So because I call this mass 1, I'm going to call this object number 1 over here. I'm going to call the one on the incline object number 2. Okay. And then I'm going to write a net force equation for object number 1, and I'm going to write a net force equation for object number 2. And then I'm going to solve them and get an equation for the system as a whole. Okay. So over here I have object number 1. And if this box is going to move down, the helping force is FG1 because it's pointed in the direction. So I have FG1. And the hindering force is tension because it's parallel but pointed up. Okay? Minus tension. And that equals M1 times the acceleration of the system. Okay? Now we're going to do the same thing, but now we're going to look at object 2, the box on the incline. So this is object number 2. And if it's going to go up the incline like this, here's my direction arrow. My helping force is tension because it's parallel to and pointed in the same direction. So tension is parallel here. And then my hindering force is definitely friction. Look, it's parallel and pointed in the opposite direction. So minus friction. And then there's one more. Don't forget about it. We have had this as a helping force before, but in this case, it's a hindering force. Check it out. FGX is also pointed down the incline in the opposite the direction of motion. So it's going to be minus FGX. And that's FG2X. And that's going to equal M2. times A. So this is a valid net force equation for the hanging object, and this is a valid net force equation for the one on the incline. Now I'm going to draw a line, and I'm going to write the equation for the system. Okay. So one way I can do this is I can write all of these out in a nice big long line, and what I would find out is that I have minus t and a plus t, and when I have, say, -1 plus 1, what do? They total to 0. So negative t plus t gives me no tension. It cancels out. And if you set up your net force equations correctly, your tensions should drop out of the system equation. Because really, when we're looking at the system equation, we're not looking at the internal forces on the system, we're looking at the external forces. So I'm going to cross the tensions out here and not even worry about them, because I can see that they're going to cancel. And so what I'm left with is Fg1 minus force of friction minus Fg2 in the x direction, and that's going to equal the sum of mass 1 plus mass 2, because it's both of them moving together, right? So I have to keep them together. And then it's one acceleration because they're moving together. And this is the equation I'm going to solve for the acceleration. No biggie, so let's get to it. So Fg1, if you remember, it's just mg because there's no angle. So this is going to be m1 times g. Then friction is going to be mu times Fn. And then Fg2x is, well, it's the opposite side of theta, so it's going to be m2g, sine theta. And that is going to equal m1 plus m2 times a, right? Cool. All right, here we go. What is Fn equal to in this case? Well, I don't have any other parallel perpendicular forces to the incline, so it's equal to Fgy, which is mg cos theta. So my equation now is m1g minus mu m2g cos theta minus m2g sine theta is equal to m1 plus m2a. All right, and from here it's just to plug in numbers. Essentially, we're going to solve for a so we can divide by the sum of m1 plus m2. But that does not mean that your masses cancel out, so don't drop your masses out, because this is the sum of the two, and we don't have that term up here. It does drop out here. Okay? So now I'm going to put numbers in. So now I have 8 times 9.8 minus 0.22 times 8 times 9.8 times the cos of 37 minus 8 times 9.8 times the sine of 37, all over 8 plus 8, which is 16. Okay, so this is over 16. And that equals A. Now when I do this math, I get 78.4 here, minus 13.77 minus 47.18 equals A, and divided by 16 equals A. And I get 17.45 divided by 16 equals the acceleration, which equals 1.09 meters per second squared. So there's the acceleration of the system. Now, sometimes the problem stops there, but more often than not, they ask what the tension in the string is. And this part is a little bit easier, I think, because you already have the net force equation, and you just have to pick the one that's easier. So if you remember back up here, where we made our net force equations for the individual objects, they're still valid. We can use one of these to solve for tension. I can't use the system equation because tension doesn't exist in the system equation. But I can look at these and say, well, there's tension here and there's tension here. And I might say, well, which one is simpler to solve? And number one is simpler to solve. So I'm going to solve equation number one using the acceleration I just found to find the tension. So taking equation number one, I have Fg1 minus tension is equal to m1a. And Fg1 I found out is over here, mg1g 78.4. So this is 78.4 minus tension is equal to 8 times the acceleration, which is here, 1.09. And when I get that and I do that math, I'm going to subtract to the other side and then subtract this value from 78.4. I get the tension is equal to 69.7 newtons. And if you were to solve equation number 2 for tension, you should get the same value, or pretty darn close. All right. So that's a fun problem. There's lots of variations. This could slide down the incline and then friction would point up the incline. You could have 2 boxes on here. The pulley could have mass. There's lots of ways that we could change this on you. But it's all the basic same setup. Always start with your free body diagram and then find your system equation. All right, hope that helped, and I will see you in the next video.